Hi everyone, this is the Applied Statistics in Healthcare, and this is the third session of Logistic Regression. And in session 3, we're going to look at prognostic or predictive models, and we're going to examine topics of data reduction and validation, as well as observed expected ratios and excess deaths. Our second case study will be on a 30-day mortality after an acute myocardial infarction, in other words, a heart attack. And so we'll go to that slide now. And again, in session 3, we're looking at prognostic modeling, and it's more commonly referred to as predictive modeling. And that consists of, in this session, model validation, hierarchical cluster analysis, model approximation, fast backward step-down regression, tenfold cross-validation, and observed expected ratios and excess deaths. And our case study is in predicting 30-day death after a heart attack. We'll begin with a larger model with more predictors, and our model will be death on the 30th day by the following predictors, and we're going to end with a smaller model, and that's again death at the 30th day defined by about 10 predictors. And here's a slide on the background. The overall goal is to develop a regression model for 30-day mortality after an acute myocardial infarction. More information can be found at this website above. But in this data set, we have 785 patients, of whom 52 died. And we would also say that 733 survived, and that gives us a mortality rate of 0.07. In the first session, we reviewed in Frank Harrell's book, Regression Modeling Strategies. We reviewed his findings on determining the number of predictors we would use in a model. And so because our data for our outcome of 30-day death is coded as 0 or 1, what he suggests is to use the smaller of those two categories. And so in this, with 733 that survived and 52 that died, we would use that number 52, and then we would divide by 15. And that would give us the number of predictors that we should use in our model, or at most we should use. So with 52 patients who died, if we were to divide that by 15, that would suggest 3 to 4 predictors. And in this data set, we have a total of 20 predictors, and we have 18 described in the paper that we see here. So again, we should probably only use about 3 to 4 predictors in our model, but we're going to look at the situation in which we're given more predictors, and because we're looking at because we're doing what's called predictive modeling, we would want to make sure that our model holds up in the future. In contrast to a diagnostic model or an explanatory model, in which we really want to explain what are the underlying causes or factors that impact our outcome. Rather than doing that, what we want to do is get predictions for patients we haven't seen yet. So we may develop the model that we're looking at, we may develop today, but we're going to want to use it on for example, hospital patients that come in each month, and we would want to use it for at least the next full year, and then at that point we'd recalibrate it, which we'll explain later, but we want to make sure that our predictions are not wildly off than what we anticipate them to be. In a diagnostic model, we're concerned more with data that we've seen in the past. Maybe this data might come from the previous years, and we're only interested in explaining the effect of our independent variables or our predictors and that relationship they have with the outcome. But for predictive modeling, we want to make sure that our predictions hold up over time on data that we haven't seen yet. So what we're going to cover in this session is we're going to review the importance of overfitting, and that would be overfitting happens when we use too many predictors, too many variables in our model, and that leads to predictions that are less likely to hold up over time. So we have to be really careful about how many predictors we use. It looks like it could be about 3 to 4, but we're given a data set that has 20 in it, and this may be a case where all of our stakeholders consider those all 20 as important predictors. So we need to figure out which ones are the best, are the most predictive, and what steps we need to take. And that's what differentiates predict modeling with explanatory modeling. We want to make sure that we've developed the most parsimonious or efficient model that we can. Okay, so here are the variables. The day 30, that's the outcome, 30-day mortality. It's coded 1 if they do have a 30-day mortality. We also have the variable sex, which for females, their values are coded as 1, and for males, their values are coded as 0. We have age. We have age 65, KILLUP, which is a KILLUP class of measure for left ventricular function, class 1 through 4. And we have various other predictors like hypotension, heart rate, and heart rate, the tachycardia with the pulse greater than 80 is coded as 1. So it's not a continuous variable, it's a 0, 1 based off the pulse score. Greater than 80 equals a value of 1. We have variables like height and weight. We have hypertension. We also have smoking, lipids, and then at the bottom we see we have time to relief of chest pain, which is greater than an hour. If so, then it's coded as a 1. And here's a data summary of our main predictors. We see that on the top left, our outcome of day 30 shows that we do have a 6.6 mortality rate, and you see that in the mean equals 0.06624. Most of our respondents are males, because sex is coded as 1 for females. We only have about 26% of our sample made up of females. The average age is about 62 years. And then we can see the other values there. TTR, which again is time to relief from symptoms. 1 if it's greater than 60 minutes, and we see that the average is about 0.5. So about half were above the 60-minute mark and the other half were not. And here's our first regression model, and we used all the predictors in our model, in our data set. The model performs well according to the C statistic, but we want to know how valid are the results. In other words, how will it hold up over time? Or we might ask, is there overfitting? And so we see a value of C that would indicate a very good model fit. Again, the C statistic is also known as the area under the curve, or the AUC. 0.836 is a really good number. If we scroll down our different predictors, if we go to that far right column and focus on the p-value, that would indicate anything below 0.05 would indicate what we'd consider a low chance of us being wrong about that being an important finding. So we see that age meets that 0.05 alpha level. Hypotension's close. Heart rate is considered statistically significant. The previous myocardial infarction is close. We'd consider that marginally significant. And we see when we get to the bottom, time to relief of chest pain, that is what we call statistically significant at the 0.05 level. We don't actually, if our clients found that these are all clinically relevant predictors, then it's something we should consider keeping. I'm just scrolling through based on the p-value, that we often put a lot of emphasis on the p-value. It's important, but we also want to make sure that we include what's clinically relevant. So in this data set, for this sample, some things might show up as significant, while other predictors that we think are important don't show up as significant. We'd want to make sure to keep things that are clinically relevant, but we'd also want to make sure we have things that are statistically significant, and we want to make sure that we consider that having in these other important predictors actually gives us more precision. So it may not be statistically significant, but for a small part of that sample, it may be statistically significant and statistically substantial. So some things that are that don't show up as significant may be because it may be significant, but just a small part of the sample. So if we had our sample made up of just that smaller subsample, then we would probably get statistically significant results. So there's a variety of reasons we want to keep in variables that may not show up as statistically significant at that 0.05 level. But we're going to go through and figure out what things we really need versus the ones that the predictors that we could remove and still get a very predictive and accurate model. And so here we're looking at model validation, and the reason we are is because model validation provides us a way to determine how predictive our model will be over time. So we previously used the C statistic or the AUC as a way to gauge model performance, but model validation is a way to do that so we can predict on future outcome. And the way we do that is that we hold out some of our data set, the sample that we're looking at currently. We hold out some of it to develop a model on what we call a training set, and then we we make predictions on the other half that we've held out, called the testing set, and then that gives us an idea of how well that model performs on future data. So we develop the model on, say, half the data, and with the other half we test out those predictions on that second set of data, and that gives us a good idea of how well it will perform in the future. So we have two different things that we look at. One is calibration, and that's how well it predicts in the overall sense, how well it predicts our outcome, and then the actual outcome versus what we predict. And then we have something called discrimination, and that gives us an idea more at a finer level how well the predictions work for each individual respondent. Calibration is more of a high-level statistic on the overall sample, while discrimination focuses on an assessment at each response level, each case, each level, each row of data. And so it gives us a finer view of that performance. So how we describe calibration, models Models are calibrated to a data set when the average of their predicted values matches the average of the actual outcomes. Models should be recalibrated if the calibration weakens over time, especially if the model was developed outside of your organization. And so the model predictions can actually can become off if we actually make change. So if we're making positive change in an area that was important to the model, then we can see that that positive change actually give us a weaker model. For example, hand hygiene. That's one thing that we know. If you wash your hands, then that would greatly reduce the chances of infections in the hospital. So if we have a very low hand hygiene rate for our clinical staff, if they're not washing their hands or using hand sanitizer as frequently as they should, then what we often see are higher numbers of infections. But what happens if we get our hand hygiene compliance, if we're washing our hands 99% of the time? If we went from, if our current level is at 50%, we're only doing it half as frequent as we should, then that variable will likely be considered a very important predictor, and what the value is for that could significantly predict who's going to get an infection. But if we get to that from 50% and we move it up to 99%, then that hand hygiene variable will be a lot less important. So if you have predictions that are heavily based off of your hand hygiene level, but you move it up to 99%, then that hand hygiene variable will be less predictive, and your the infections that you do get, even though they're going to be fewer, they're going to be based on other things. So other things are going to look more important at that point compared to what they look like before. And so that's not to say we shouldn't focus on hand hygiene, keeping our levels up, but it just means it's not as predictive anymore since everybody's doing it. Since there's almost no variation in that, when you have a variable with almost no variation, then it becomes less predictive. When you get to 100%, if you try to run a logistic regression, it'll actually crash the software, because in a regression you can't have a predictor that has identical values. There's no variation associated with that predictor. So as we improve, we actually need to, that's another reason we need to recalibrate our model. Overall calibration error, that's one way to examine calibration, is to look at the average of y. That's the average of the outcome. In our sample, that is 6.6% or 0.066. And then we'd minus the average of our predictions. And so we would, if our average for our predictions was 5.6% or 0.056, then the average of y at 0.066 minus the average of predictions at 0.056, that would come out to 0.01. So that would be a small overall calibration error. It's not great, but it wouldn't be that high. And another way we can assess calibration is through a calibration curve. It can help visualize the calibration. We can select the deciles or quantiles of the sample and plot the average outcome and predicted values in each group. So in other words, we would sort all of our predictions. We'd go from lowest to highest, and then we'd break it up into 10 equal groups, or we could do 5 as well if we had a small sample. But say we break it up into deciles, the 10 groups. What we do is calculate the average of y and the average of the predictions for each decile. For each of those 10 groups, we would do that, and we would plot how close they come together. So if we have a nice straight line where our actual average of y is identical to the average of our predictions, then that would show that we'd have perfect calibration. We don't, it's very rare to get perfect calibration, but we'd want to know that we're doing well, especially on the key deciles. So if one decile has is represents the kind of result we're most likely to see, then we'd really want to pay attention to that. And if there's just a really high decile, or maybe a group that we're not a decile that we're not as concerned, then maybe that would be something that we'd be less concerned about. But it gives us a visual representation of that calibration by instead of looking at the overall calibration error, which represents all patients or all cases, we can do a calibration curve and see how it looks for our different for 10 different groups based off of their prediction score. And so that brings us to discrimination, and that is the extent to which a model predicts higher outcomes for those with actual higher outcomes. This is the area under the curve in R squared. We can also use MAD. This is an individual level summary. Just to restate that, discrimination is an individual level summary. While good model calibration is desirable, discrimination is usually more important. For example, if the average length of the stay is 3 days, a model that assigns predictions of 3 days to everyone is perfectly calibrated. So if we made a prediction that all patients would have a 3-day length of stay, we technically would get a perfectly calibrated model. But a model that assigns 3-day predictions to those who actually stay 3 days, while just assigning 1-day predictions to those who stay only 1 day, that model provides more useful information. And we can see that with greater discrimination, that would be a bigger concern when we're doing predictive modeling, because in that case we're assigning predictions to each individual patient or case. So model discrimination is actually something we would be more concerned about when we're doing predictive modeling. And so here's a look at some model validation results. I did what's called a split half model, or a split half validation. And so what that means is that's the example that I mentioned earlier, where you randomly split half the data. So maybe you take 500 of 1,000 rows, and you develop your model on that random 500 rows of data. And then once you have developed the model, then you test it out on that second half, the other 500 rows of data. And so so we see on the top this comes from the RMS package. So there are other ways to do model validation, but the idea is that in this method, you train the model and then you test it. In the RMS package, they have what's called the index corrected value. And so what that is, it would indicate the optimism minus your original model. But what you can do, what's more commonly found is you have a training set and you have a testing set. And that would be the third and fourth columns in this data. So one way to do it is to just develop your model in your training set, and then you can use the results from your test set to determine model validation. And this, what I get from the RMS package is that that difference between the two would indicate optimism. So that optimism is subtracted from the original, the index.org, and what you're left with, the index corrected, is the bias corrected validation, and that would represent what your model performance really is. So we see that on the left side in that red box, those represent our primary validation statistics. The dxy is a transform value of the C statistic, or the area under the curve. The area under the curve ranges from 0.5 to 1, and because it doesn't use that full range of 0 to 1, the dxy was created to convert that area under the curve into a range that goes from 0 to 1. But we can convert it back to the C statistic, or the area under the curve. They're the same thing. So if we take our area under the curve, or I'm sorry, the dxy of 0.314, divide that by 2 and plus 5, that gives us a validated, that gives us an area under the curve of 0.66. So originally we had a value of 0.84. So we see a significant drop in performance after we validate. And that's due to having too many predictors in our model. So this is this big drop in the area under the curve represents significant overfitting. It's just not performing as well as it should. So this would be a bad model to use in predictive modeling. We'd probably find out over the year that a lot of patients that we wouldn't have predicted as having the outcome of 30-day death do actually have that outcome. They do have death within 30 days after their heart attack. So that would be the outcome of using a model with overfitting, is that we wind up not predicting as many 30-day deaths as possible. So when we predict 30-day deaths, we're actually giving our clinical staff an opportunity to act or intervene on those patients likely to die. So there would be serious consequences or we would, again, a predictive model would provide us with more helpful information, so we would miss out on the opportunity to help more people. So the dxy and r-square are model are discrimination indexes. The intercept and slope refers to the model calibration. And so ideally an intercept equals 0. That would mean that it would cross the intercept or the y-axis at that 0 point, and our slope would equal 1. When you have an intercept at 0 and a slope equal to 1, that would represent like a 45-degree angle, a straight line. And so what we see with our intercept and our slope, they're off, so those are not good signs of model calibration. And we may want to check to see if it was a bad split and try a new seed in the random number generator. So I mentioned that we randomly sample half the data set and then save the other half. So to do that, we need a random number generator. And so it just gives us a starting point in how we collect or how we get those random samples. One thing that we can do when we're doing model validation, and this is for R or SAS or any other software you're using, is to try a new random seed number. And you can see if that can help, and if the improved results seem consistent over a variety of other random seed numbers, then you should feel okay with using it. But for this, it didn't really seem to improve after I used different random number seeds. Okay, so we know we have too many what are called degrees of freedom, and that's really what that number 52 divided by 15, the 52 deaths divided by that number 15 to help us get an idea of how many predictors we have. So what we can do instead is we can combine various predictors that are related and also measuring maybe the same thing. So what you can do is say maybe we started with 20 predictors, but say if we find that 5 of our predictors are describing the same type of characteristic, maybe it's maybe it's about the person's physical stature, then what we can do instead of using 5 or 6 separate variables, we can combine them, and we would just only use and so those 5 or 6 variables would represent one variable, and so that would give you a lot more flexibility in running these models, especially if those predictors are similar and they're tapping into the same features. So methods such as hierarchical cluster analysis can greatly improve model reliability because it reduces collinearity. However, there appears to be only pairs of variables that highly cluster together. In other words, there's not much benefit of making a composite variable from only 2 variables. Because of the poor model validation, we'll eliminate multiple predictors instead. So we see that how we would interpret this graph is that the variables that link together, so this is sort of like a family tree, so the things that link together are the things that are related to each other, and if we scroll over to the left, the further down that these are, the greater that correlation. So for example, on the bottom left we see that sex and height are correlated, and that correlation level is about 0.45. So that's a pretty good correlation. However, it just represents 2 predictors, and maybe something that's not too highly correlated with the outcome. So this is actually the best option that we have. We may even want to consider combining it with weight. That WEI represents weight. So if we know a patient's sex, height, and weight, that gives us an idea of maybe their stature, I guess. But what we end up probably seeing is that more males may be taller and heavier than females. So that's maybe not the most useful information for predicting 30-day death. So because of that, and we know that the other things only pair up, we don't see 5 or 6 variables linked together, this may not, hierarchical cluster analysis may not help out a lot. So we're going to think about reducing the number of predictors. And one way we can do that is through model approximation. And this is in the RMS package. What we do is we can reduce variables and maintain 95% of the predictive power of the gold standard model. And so this is in the RMS package. The idea is that not all variables are created equally in terms of how well they predict. So it may be possible to drop many variables and still retain a very high predictive power. So the goal would be to reduce as many predictors but maintain 95% of that gold standard model. And the gold standard model is the original model that we came out with. So in the bottom right, we have a red triangle, and that points up to about the 8th variable. So you know you can drop these first 8 variables and still have about 95% of the predictive power of that original model. So you can click this link to learn more about model approximation. And I forgot to mention that for this hierarchical cluster analysis graph, the dendrogram, you can click this link to learn more about data reduction. Okay, so let's go back to our model approximation. We can see that these are the variables we can delete without losing any substantial predictive power. So height was one of the variables that we could drop, and if you drop all 8 of these variables, you'll still be left with at least 95% of the predictive power in your model. So these predictors are probably not that helpful in predicting 30-day death. And another approach that we have in the RMS package is to use the fast backwards step-down regression. And that's in the Frank Harrell book. Actually, so is the model approximation. And for how it works is that it uses AIC-based suggestions on the far right, and then that's that column AIC. It suggests removal of predictors that don't have a significant change in the what's called the Akaike Information Criterion, or the AIC. So we can drop all of these predictors, all but 2, and it gives us a model that's not significantly different in its predictive power than the original model. So on the top portion, those are the variables that we can delete, and we can see in that second column from the right that it doesn't substantially change the predictive power of that model. It leaves us with just 2 variables, and that's age and the heart rate. So these 2 variables are not significantly different than all of the variables that we originally began with. And it says the 2 predictor model, the area under the curve, or C statistic, is 0.79 and validates at a 0.78 level. So the model validation is pretty close to the actual model. This performs well. We do have something in SAS that we call stepwise regression. They give you at least 2 options. One is forward and the other is backwards stepwise regression. The forward stepwise regression has a number of issues that make it not a good choice. A better choice would be the backward stepwise regression, and that would be a similar idea as this approach. Just to go back to the model approximation, what you can consider an alternative would be to use something, if you reduce predictors, that leaves you with about 95% of the same area under the curve, then that would give you an approximate model. So if you're not using the RMS package and you want to do something like this in SAS, then you can probably reduce it. You can probably approximate your model if your reduced model has 95% of the predictive power. And an equivalent of this is in SAS would be the backwards stepwise regression. Okay, so now we have our improved model. What I did do is I went with the approximated model, which gives me 10 predictors. On the top right, we have our C statistic, or the AUC, the area under the curve, and that comes out to 0.830, and that's only a little bit lower that's just only 0.006 points lower in this new improved model, or this improved model. So that predictive power is that we see is about the same. And then when we do a model validation, when we look at the DXY, that very top row, and we go to the index corrected column, that gives us an idea about what the difference between how the model looks like after we do our training and test sets. That comes out to 0.576 on the DXY level, and that gets converted to a C statistic or an AUC with this formula, and that comes out to 0.79. So that is pretty close to that 0.830. They're not too far off. That would be a good option, a much better option than using all of the predictors. And so the reason that we have this better model validation is because we have much less overfitting. And the reason we have much less overfitting is because we have fewer variables in our model. Sometimes based off that combination of variables, we might get a lucky value for one of our cases that did have 30-day death. Just kind of a weird combination of predictor values may have happened for a value for one of those 30-day death cases, and that would give us a higher area under the curve. But because those are very rare, odd combination of values, you don't expect to see that happen often. So in the future data, we would find out that our area under the curve doesn't hold up. And a famous example of that would be when Google tried to predict when they tried to predict flu cases. So that was actually pre-COVID, and their original data set, they developed a model with a lot of overfitting, and when they tried it out the next year on actual data, it performed really poorly, and so they stopped using that model, fortunately. But that's an example of overfitting. We've reduced our variables here. We've improved our model validation because we took out variables that weren't important to the model, that may have just wound up being a lucky combination of predictor values that gave us an AUC that was too high. So in summary, we have less overfitting because we have less variables, and now that means we have better model validation, and when we use this model in the future, it's going to hold up better, and we're going to have better opportunities to help our patients. And so in this model validation, I used a 10-fold cross-validation, and the cross-validation appeared to provide more stable results. I compared 10 different random seeds, and it was more stable with 10-fold than 2-fold validation. The sample size may have been too small for the split half method. So if you have a smaller sample, something like a 10-fold cross-validation would probably be a better option for you than, say, the split half method that just has one training set and one test set. Okay, so now we're going to start to explore some of those predictors. Although for a predictive model, we're not necessarily concerned with explaining each of these predictors. It may be helpful to know if is it one of these predictors or all of them that equally contribute to the model, or maybe just some of them. So still thinking back to that's the suggested number of variables, which is about 3 to 4, based on our low number of deaths. we may want to still consider, can we reduce this model more? We know that reducing the number of predictors helped, but are there certain predictors that that our understanding of 30-day deaths are based on, or are they equally spread out among all 10 variables? If all 10 variables have the same variable importance, then I may consider, I'm more likely to consider leaving the model as is. But if it's only a few, then that might be a chance for us to reduce our variables even more. So what we see in this model summary is that age, heart rate, killip class, and time to relief of chest pain all increase patients' odds of 30-day mortality. For example, going from a lower range of 43 on age or to 71 years. Actually, it's from, I think, 53. 53 to 71 years represents about a 5-fold increase in the odds of death. So we see that red dot falls under 5, and that gray vertical dashed line that represents no difference is not found within that normal range of the age effect. So that's a very significant finding, that increasing in age increases someone's chance of 30-day death by 5 times. But for these, so these 4 predictors, we actually do see that difference where it's a significant difference, because we can see that 95% confidence interval does not contain that vertical dashed line. So it looks like that we do have some predictors are going to be more important than others. And so when we look at variable importance, we can see that again that those 4 predictors at the very bottom, age, heart rate, time to reducing symptoms, and the killip class are our most important predictors. And how we can read this graph is that the black dots furthest to the right are the most important predictors. As a fast backward step down regression suggested, age and heart rate were the most important predictors. But we do see that killip and the time variable are also the next most important, and they're significant at the 0.05 level. So if I had to pick 4 predictors for us to look at instead of 10, it would be these 4. Of course, I'd want to get the clinical input from our clients, but just based off of statistical values, I'd pick these bottom 4 as the most important predictors. And so just to give us an idea of what the how the trends look, we can see that higher killip values on the top left indicate greater chances of 30-day death. We see some group differences, but on below that on the bottom left, we see that for age, that's a pretty steep trend. So that would indicate even a stronger relationship with this variable and the outcome. So as patients age, their chances of 30-day death increase even more. And in this graph, we have our partial prediction plot using probabilities instead of logits in this previous graph. So we're going to see a little bit of a bend in our trend lines, and that's because we are now looking at probabilities on the y-axis. They go from about 0 to 0.20. Because we're doing logistic regression, as we get closer to the extremes of 0 or 1, we see that those lines get pulled in more. Okay, so now we've decided to run our model just using 4 predictors based off of that 52 deaths divided by 15 rule. And we see that on the top right, our area under the curve, our C statistic, is 0.815, so it's 0.82, and that's pretty close to what we had before. For the 10 predictor model, it was 0.83, and now we're only off by about 1 point. And that still gives us a good model result initially. And when we look at our validated area under the curve, we see in the top right it's 0.78. So that, again, this is only about 1 point lower than that 10 predictor model. So that that would make us a little more likely to use this one, because with these 4 predictors, we get something very close to that 10 predictor model. And knowing that we are probably using too many predictors in our model, this might make me lean more towards this 4 predictor model. The validated model stays closer to the original area under the curve. If more variables are considered key study questions, suggest doubling sample size to get the 10 predictor model. So if our clients really want to use those 10 predictors, what we can do is suggest that we wait until our sample size has doubled. And if we do that, then we're going to probably have 100. We may have 100 divided by 15 rather than 52 divided by 15. That could be a tough decision to make if this data took a long time to collect. If it didn't, it would definitely be worth waiting to collect more data so that you can test those 10 predictors if they are considered critical to the study findings or to the model predictions. Okay, so another thing that we can do is, now that we have that 4 variable model, what we can do is look closer at the calibration curve. Because the cross-validated calibration curve produced trends with less focus on the range, with the majority of predictions, we'll examine this traditional calibration curve. I have an option in my Shiny app to do a calibration curve using cross-validated results, but I just want to use this one. It's a little bit easier to focus on the area that we really want to. So the 4 predictor model showed better calibration in 8 of the 10 deciles below when compared to the 10 predictor model. This supports the model with 4 predictors. So this is a calibration curve for the 4 variable model. I did it for the 10 variable model, and we see that in this 4 variable model, we see that these blue dots that represent the actual averages for each of these different deciles based on the predicted score. With the 4 variable model, we see that these blue dots are closer to the red line than if we had the 10 variable model. If we had the calibration curve for that, some of these blue dots would appear further away than what we see in this graph here. For example, on the far right, we can see that for our top decile, if we were to line up all of the predicted values and just take the top decile, if we lined them up from lowest to highest, we would look at the 10% of the sample with the highest predicted probabilities. And for that top group, that top bin, that 10th decile, that average on predicted values is 0.29. These are on the x-axis, we're looking at means of predicted values in each of those 10 bins. And the actual number, that would average 0.28. So that 0.28 on actual deaths is very close to our predicted level of 0.29. And we see that for each of these different deciles, the predicted number is close to the actual number. So that's a good sign of model calibration, and that's another bit of information that would help support our reason for having a model with 4 predictors instead of 10. And now we can look at calculating observed expected ratios, and excess death. For a sample, we can calculate the total number of deaths by summing up all of the probabilities returned from our model. So if we wanted to say in our sample, if we sum up everybody's probabilities, that should equal the number of actual deaths that we have. For future samples, we do something similar. We calculate predictions from an existing model to determine the predicted deaths. So the observed expected ratio from our sample is 52 divided by 52, and that equals 1. Because our model is based on our sample, the OE ratio equals 1, and that would always happen for whatever data set you work off of. Maybe it would only not be identical if there's a rounding error, but when we look at future data, we wouldn't expect our observed number of deaths to equal our expected number of deaths. So the observed expected ratio is the number of deaths that we actually saw, and it's divided by the number that we would predict. So say if my sample has, if I'm predicted to have a chance of 0.05, and maybe your chance is 0.02. If we were to sum up everybody's predicted probability, we have 758 rows. If we were to add up the predicted probability for all 758 rows, it would sum up to 52. But when we look at future data, that won't be the case. So the observed death divided by the expected death in future data, that would give you the observed expected ratio. It would be two summary statistics of the entire sample, one divided by the other. In excess death, we would use again those summary statistics of the full sample. The observed number minus the expected number would give us the excess death. In this sample, we have 52 minus 52, so it's 0. Again, the reason is because we are using the data set that we developed the model on, and for that it's going to be perfectly calibrated, so those two numbers are going to be identical, or they're not going to be identical, but they're going to be 1 for the observed expected ratio and 0 for excess deaths. If next year's sample has 81 observed deaths and 78.7 expected deaths, if we're looking at a future data set and it has 81 observed deaths and 78.7 expected deaths, the observed expected ratio equals 1.03. That's 81 divided by 78.7. And excess deaths equals 2.3. That's 81 minus 78.7. So when we're working with observed expected ratios and excess death, we're looking at those overall numbers, and the observed part would be just the number of deaths that we have, and the expected part would be those predicted probabilities summed up together. And that's it. That's the last session. Next week we're going to do session 4 on prognostic modeling, and that's going to be how we implement a predictive model and put it into use. Thank you.